Alright, here we are back in a review portion of Chem 230, and one of the big questions is what is an orbital? And what is an orbital? And the original idea came from something called Schrodinger's equation, which is a whole bunch of terrible math and physics that we don't have time to get into. And I say terrible just because a lot of people can't do it, but it's actually very beautiful math and physics that really gave us a lot of insight into the electrons and the electron behaviors. When you solve the Schrodinger's equation, you get something called a wave function. And if you graph the wave function, you get an orbital. So in a really simple sense, an orbital is a graph of the wave functions and the wave functions are the solutions to Schrodinger's equation. Now when you go ahead and interpret this and think about it, the graphs of the wave functions describe the region in space where an electron resides as a wave. So the region in physical space where an electron resides as a wave, and we used to think that an electron was a particle, that it does have a little mass, and that it would bounce around like a ping pong ball or whatever and bump into things. But in reality, especially within an atom, electrons behave as waves, and the thing that governs their behavior more than anything else is interference patterns, constructive and destructive interference, and those types of things. And so how these orbitals interact with each other and what types of interference really governs what's going on with electrons. And most of that is well beyond the scope of this course. So you might ask, well, that sounds really complicated and there's lots of math and physics that goes into understanding it. If you just know these definitions of what orbitals are, that's a good basic understanding for an introductory or fundamental course. So an orbital is something that comes from solutions to the Schrödinger equation and graphs of those wave functions. And it's believed to be, in terms of interpretation, the region in space where an electron resides as a wave. So that's pretty cool. And one of the things that you should definitely recognize would be sketches of wave functions. And there's a whole bunch of different solutions, and some of them get really complicated and super interesting, and they're really beautiful. But the first one is just a sphere, which on a two-dimensional sheet of paper I'm going to draw as a circle. And then the next one, they've always called the dumbbell. I don't think this looks like a dumbbell. It looks sort of like an 8. And there's 3 of these that are at different orientations, all perpendicular to each other. So you'll have the X, Y, and Z orientations. So this one is going to protrude towards us. So this emphasized lobe here is pointing straight towards us. This dashed lobe is pointing straight behind us. So we have these 3 orbitals, which are exactly the same shape, they're just pointing in different directions. They may not look the same shape as I draw them, and we traditionally draw them thinner and longer than they really are if you graph the wave functions. And then there's other ones that are more complicated. This one looks like a fused double dumbbell kind of thing, or a 4-leaf clover. And then there's one that looks sort of like this, and I don't know why they call them dumbbell shapes. They don't look like dumbbell shapes. They look like infinities or 8s, depending on which way they're aimed. But one of them looks like a larger 8 with a hula hoop around its waist. So there's these different drawings, and if you see these, I would expect you to look and say, holy cow, those look like orbitals. So the wave functions, or graphs of wave functions, or sketches of wave functions, are representing orbitals and the physical space that electrons occupy. This is the shape of an s orbital. This is the shape of a p orbital, and we might call this one py because it's sitting on the y-axis mathematically. This one we might call the px because it's got this p shape, but it's sitting along the x-axis, and then this perpendicular to the paper one would be the pz because it's sitting on the z-axis. So different orientations, different orbitals within a sublevel, and if you've done some quantum mechanics stuff before, this should start to click that there are 3 different p orbitals within a p sublevel. It's something you've probably heard before. These guys are d orbitals, and those are 2 of the shapes. This one goes along 4 different independent orientations, and this one's sort of mathematically a complicated combination one that gives us our 5th. So there's one wave function that looks like this in each energy level. There's 3 that look like this, and there's 4 that look like this one in different orientations, and 1 that looks like that. And that's, again, maybe a little above and beyond the introductory course, but when they gave me a really brief introduction to wave functions and orbitals, so we can call these orbitals as well, they gave me so little information I had absolutely no chance of understanding where it came from, where we were going, or what I was looking at. It was just some new confusing terminology that I got to hear in sentence form. So this hopefully gives you a little bit of background into where do wave functions and orbitals come from, mathematical solution of the Schrödinger equation, which was put together to understand electrons and their wave behavior. And these represent the physical space that you can find electrons in. And as we start talking about electron configurations, hopefully this will click and make some more sense. If you have any questions, feel free to shoot me an email or ask in our live online session class, and I will try to help you as much as I can.